Hey, second row. Singing, no more. All right, ladies and gentlemen, class recording has started. So, way back at the beginning of chapter 27.1, we talked about the postulates of relativity, basically the ground rules that we are working under. And there are two ground rules that Einstein talked about when coming up with his theory of relativity. First, the equivalence of physical laws, where said the laws of physics are the same in all inertial frames of reference, right? That's the example, the demonstration of me walking around with the tennis ball the whole time, right? If I'm standing still, it goes up, comes right back to my hand. If I'm walking, it goes up, comes right back to my hand. As long as we are in inertial frames of reference, right? Constant velocity. The second postulate, constancy of the speed of light, that no matter where we measure it from, light will always come up with the same speed, that 3.00 times 10 to the 8th meters per second. Okay? So, these two rules get us to all the weird things that we've talked about over the past couple of days, like time dilation and length contraction and relativistic energy, E equals mc squared. Okay? So all these weird things that only start taking effect once we start going close to the speed of light, right? Because of that weird square root of 1 over v squared minus c squared. Okay? Good? All right. But all of these ideas are part of Einstein's theory of special relativity. And it's special in that it applies to things moving in inertial frames of reference, constant velocity. But Einstein knows that you can't make up a rule or a law that only applies to certain instances, right? If you're going to make a law that defines the universe, it's got to work no matter what, all right? So he has to figure out how to explain acceleration. And so he starts working on his next theory, the theory of general relativity. Okay? All right, so there's one acceleration that we deal with all the time. What is that one acceleration that we deal with all the time? Gravity, right? So he starts with gravity. In that, he pictures, and we get into Einstein's thought experiment, right? So, here are three pictures that explain Einstein's first thought experiment. Okay? So, if I take this tennis ball, this is the picture on the right, if I take this tennis ball and I drop it, what happens to it?
Comes back up.
Really? What does it do first? It falls, right? And as it falls, we know that it experiences an acceleration of 9.81 meters per second squared, right? And that acceleration applies whether I drop the ball straight downward or whether I toss it sideways, right? The horizontal motion doesn't affect what's happening vertically. It goes in that parabolic path. Great. Okay? All right. But, middle picture. Einstein says if we go to some place that does not have gravity, and I let this ball go, what will happen to it? It'll stay there. Unless. Well, no. Okay. Well, yes, I guess I'll give you that. But his idea was something different. Unless, let's say this place where we've gone that doesn't have gravity, all right? So he pictures, let's say we're in an elevator. Okay? No windows, no doors, can't really tell where it is. Okay? If there was no gravity, the ball wouldn't do anything. But let's say the elevator started accelerating in the upward direction. Okay? If there's no gravity, but the elevator is accelerating upward, what's going to happen to this ball? It's going to stay in the same place, but what's the floor of the elevator going to do?
So the ball's going to go through.
No, I mean, it's not going to go through the floor, right? The ball will stay in the same place, but what's the floor of the elevator going to do? Go upward. So what is it going to look like this ball is doing? Falling. Okay? And if the elevator is accelerating upward at 9.81 meters per second squared, and you let go of the ball, what do it look like? It's accelerating upward at 9.81 meters per second squared. Yes, I'm holding the ball, but no. Well, fine. Okay? That's fine. Okay, so it's currently accelerating upward at 9.81 meters per second squared because I'm holding it. But if I let it go, what will it do? It will not stay in the same spot. It will not stay stationary. It will keep moving upward, but at a constant velocity. But if the rest of the elevator is still accelerating, where does the ball end up? On the floor. How long will it take?
The same amount of time.
That long. Does that make sense?
Would it bounce?
It would bounce.
Oh, so it's the same thing. I was thinking that.
But still, we're talking about the dropping part.
No idea.
Okay? So,
Wait, Mr. Plan is
do this.
If it was a bowling ball,
Same thing.
and it wouldn't go through, because wouldn't it?
I mean, it
keep
might.
going and it would stay
I mean, it might, just like anything else that might go through the floor, right? So first, are we okay with, okay. Okay, well, I don't really care if you're okay with that or not. And I gave away my hard hat to the Latin people, so. All right, so, right? We good? We drop the ball, right? It accelerates downward at 9.81 meters per second squared. Yes? But what Einstein says is, you couldn't tell the difference between this ball accelerating downward at 9.81 meters per second or the floor. What was I trying to say? I don't even know. Anyway, the table, that's what I was trying to say. I was like trying to say table and floor at the same time, and that didn't work. Or the table accelerating upward at 9.81 meters per second squared. Well, what happens to the distance between the table and the ball when I let it go?
But if we're like sitting right here, we can tell it's the table.
Well, yes, but let's say, but what Einstein's saying is, it's not just the table that's rising, it's the whole room that's going upward. All right, does that make sense? And then you wouldn't be able to tell the difference between gravity or the upward acceleration of the room. Okay, does that make sense?
Okay, well, if there's no gravity and the ball's staying still,
Yep.
what's keeping you pulled down to the floor?
You're trying to stay still as well, but what runs into your feet?
Oh, the floor.
And the floor is going which way?
But how do you get in the elevator?
It's a thought experiment, all right? Let's not worry about how you got into the
You
elevator.
just swim in and
Okay.
then it comes up on
So,
you?
maybe.
Yes, because there's no gravity.
You know what? However you decide to get into the elevator, that's fine. Okay? But now we're in the elevator, right? Can you just forget about the part until we get into the elevator?
I just feel like he had to be on something to even get to that.
Well, I don't think he wasn't really concerned about the walking into the elevator and the doors opening. He's like, okay, his point being that you can't really tell that you're in an elevator. Okay? Because no windows, no doors, right? What he's saying is that if you're in a frame of reference that is accelerating upward at 9.81 meters per second squared, you would not be able to tell the difference between that and gravity. Okay?
I've come to
Okay. Do you understand that though?
Yeah,
Okay.
I just think it's silly.
All right. Well, it's not, but you know. Go ahead. Because, okay, well then let's take this to the next step. All right. So, here's the next step. Einstein says, all right, if that's the case, let's think about this elevator again. Okay? And first, the elevator is not going anywhere. Acceleration to the elevator is 0. It is stationary. You take a flashlight, you shine it across the room. It hits the wall at a spot directly across from where you first shined from where you first shined it. Yes? Okay? But if the elevator starts accelerating upward, the beam from the flashlight would not hit the wall directly across from where you shined it. Still no gravity. But now the elevator is accelerating upward. Okay? Still no gravity. Yes? Does it make sense that you would see this light beam bend this way?
I don't get it.
Well, you shine the light across the room. Okay? Let's say, there I am, right? See that sign says do not operate? Okay. I turn my light on, and it travels across the room right at the O in do. Okay? But if the elevator is accelerating upward, by the time my light leaves my flashlight and goes to there, is the O in the same spot anymore?
Yeah, wouldn't it go like with you? It would go to the next thing that's above? Like that's like,
It
I
wouldn't.
thought it would just stay like,
No.
yeah.
The light is traveling straight,
Right, so what
but
do
the
you,
wall is moving.
We were moving at the same time with the wall.
Yeah, but now I'm not connected to the light anymore. Once the light leaves the flashlight, it's on its own.
wait, what?
Say again?
Like,
Well, well, it doesn't matter exactly how fast the elevator's going, right? But if the elevator was going really fast, it would appear that the light would end up farther down the wall than it was going up at a slower speed. Does that make sense? That's not the important. That's not the important point. The important point is that if the elevator is accelerating upward, the beam from the flashlight wouldn't hit the wall directly across from where you shot it. It would hit below, because the spot that you shot it at isn't there anymore. It's going upward. Does that make sense? Just like this ball, right? If there was no gravity and I threw the ball at the wall, what would it do? It travels how if there's no gravity? Straight line, right? And it would hit the wall directly across from where I threw it. But if I threw it and the wall was moving upward, it wouldn't hit at the spot I threw it at. It would hit below the spot I threw it at. Okay?
so it's not that the actual, like the ball's still going straight, but it's just it's hitting the light.
So this is Einstein's point. Is the ball going straight and the room moving upward? Or is the ball going downward because of gravity? And the answer is, you can't tell. Okay? Jason, go ahead.
Is this only when the elevator is accelerating?
Only when the elevator is accelerating. Because gravity, so, right, if it's constant velocity,
It's gonna have the same.
right. Yeah. Inertial frame of reference, everything's the same, right? Okay? Does that, yeah, only if the elevator is moving at, only if the elevator is accelerating.
Because then the
So
elevator
does light, so does light have the same,
Right.
so does light have the same thing that the, like, when I put that it keeps up to the.
Yes. Okay.
Why would gravity affect the light?
Ah. So here is what Einstein is saying. Okay? Good transition, Grace. Good transition. Okay? So, here's what Einstein ultimately says. Okay, you get the experiment with the two balls. Okay? And you get the experiment, if you throw the ball sideways, the elevator is accelerating upward, it would look like the ball is traveling downward. And you get the experiment that the flashlight, if it's traveling horizontally, if the room is going upward, the flashlight, the light would look like it's bending downward. Are we okay with that? All those things? Okay. So Einstein says, the principle of equivalence. The principle of equivalence states that any physical experiment conducted in a uniform gravitational field and in an accelerated frame of reference gives identical results. So Missy, like we just said, is the ball falling downward or is the room going upward? You can't tell. What Einstein then implies is, if that's true, gravity should affect all things, including light. Okay? All right. So, Einstein puts this out. And again, as we discussed, Einstein does thought experiments, which are sitting on your couch thinking. Actually, that's not true. I read an article this morning that it's been scientifically proven that you actually think better when you're walking than when you're sitting. So, just throwing it out there. Okay. I mean, if you really want to, you know, so, yeah. Apparently, it's kind of not. This isn't the first person, but apparently, one of the things that's like the newest rage now out in Silicon Valley, where computers, you know, like thing, is that you go on walking meetings. That you don't have meetings like in a meeting room, like hey, let's go for a walk. Apparently, Steve Jobs used to do it all the time, and like, you know. So actually, Mark Zuckerberg, he conducts all of his interviews as walks. Like if you go to work for Facebook, like, you know, if you get hired by Mark Zuckerberg, not like if you're like some programming guy, like if you're an executive, you basically go on like a 2-hour walk through Silicon Valley, like that's your interview. So. I think the study was only about walking, but it also part of the study was they had people walk on a treadmill and walk outside. No, there was no difference. It wasn't where you were. It wasn't like being outside. It was the walking. Like the walking was better than sitting, whether you were inside or outside. And they had people sit outside and sit inside. Like they had them like work on puzzles and stuff like that. And so there you go. Yeah, like say they had the same person like do a puzzle when they were sitting in a room, do a puzzle when they were sitting outside like at a picnic table, do a puzzle while they were walking on the treadmill, or do a puzzle when they were walking outside in the park. And walking made them do better on the puzzles than sitting, and it didn't matter whether they were walking inside or outside. Yeah, I mean they said it was creative problem solving. So like well, I mean, they may have done some of that too, but it was they were working more on like creative thought. So, anyway, yeah, that kind of stuff. So, okay, all right. So, Einstein's principle of equivalence, and maybe Einstein went on walks too. I don't really know, but Einstein's principle of equivalence says you can't tell the difference between gravity and an upward accelerating frame of reference, and that means that if in an upward accelerating elevator, the light would bend downward, guess what? If it's exposed to gravity, it should bend as well. So, it's one thing to say this, but it's another thing to show it. All right? So, here is a representation of how we proved that Einstein's idea was correct. All right. Sun in the middle. You guys have this picture, by the way, in your packet. Sun in the middle, Earth down here, star up here, actual position of the star. If the sun is not in the way, if there's no sun there, it would follow the light from this star would follow this dotted line. Straight line between us and the star. Yes? Because if there's nothing in the way, it just goes straight. But when light leaves this star, it actually bends around the sun and ends up hitting us after it has bent from its original path. But our eyes and our brain, well, I mean, when we think about it, yes, but if somebody says, hey, where's that star? You would say, well, it's on this line right here. Example, let's say you're in like a haunted house or a fun house or something like that around Halloween time, and you're walking down a hallway, and at the end of the hallway, there's a mirror, okay? But the end of the hallway, right, it's really kind of like a hairpin turn, you know what I'm saying? Okay, here, I can draw a picture. Sure. I mean, all of my pictures are good, let's be serious, right? All right, so, okay, here's you, or here's the hallway that you're walking down. Okay? And you're whoosh lining down this way. Okay? And as you walk down the hallway, oh crud. Anyway, so you end up here. And you see somebody. Oh my God.
It's alright, we don't do that.
People are going to watch this on recording, all right?
Oh, you are?
So, well, I am recording it, yeah. So, you may have missed that part when I said, hey, the recording started. Okay, but- so, you see a person at the end of the hallway, but you don't know that the end of the hallway right here is actually a mirror. Okay? This person isn't actually there. No. That person is here.
That sounds
But you see them as if they're here.
okay.
Does that make sense? Your eye can't tell the difference whether you're looking at a reflected image or a real image. Well, but if it's a dark hallway and you look down the end, you don't know that's a mirror. Okay?
Just yourself.
Well, no, not necessarily. I mean, depending on where. Eventually, you might. Yes. Okay.
Oh, but you'll see that.
Okay. Okay. So you can't see or you can't tell the difference between a reflected image and a real image. And when we look at the light from this star, we don't know that it actually bent around the sun. We just trace it backwards and go, oh, there it is. Ah. You have to find a way to look at the same star when the sun is there and when the sun isn't there. Does that make sense? But the problem is, when the sun's there, you usually can't see that star because it's too bright. Unless we can block out the sun. There's only certain ways that we can block out the sun, right? In essence, yes, a big tarp, right? We call it the moon, right? So if you have a total eclipse, the sun is still there, but the moon is in the way, and it blocks out the sun's light to Earth, and you can see stars in the daytime. If you're like at the eclipse, like at the total eclipse. Yep. Yeah, like 3 minutes to figure out this star. So you take a picture of the sky, right? So in in 1917, not 100% sure on that, might be 1919, but anyway, in the late 19 teens, they did this experiment. And guess what? This star was right here at night, and it was right here during the eclipse. It's really here at night because the sun isn't there, so there's nothing for the light to bend around. But during the day, it appears to be over here because as the sun bends, or the light bends around the sun, it looks like it's at a different place. Okay? But what this shows is that gravity from the sun bends light. And if you look at a picture of the sun as it travels across the sky, right? The sun is really bright to us here on Earth, mostly because of our atmosphere, and it scatters all the light everywhere. If you get out of the atmosphere, the sun, it doesn't look like daytime. It's like a really bright star, but it's not like daytime. You know what I'm saying? Okay? It still looks, the sky looks black, but the sun is like just a really bright star. But it's not like blue sky anymore. That happens because of our atmosphere. But so if we take pictures, if we take pictures from the moon or from the space station or from the Hubble telescope, we can see other stars and the sun. Okay? And what happens is, notice, let's see if this works. So that area there, and this area here, and this area here. Okay? What are you seeing about that area surrounding the sun? No stars. And it follows the sun around. Because all the light from these stars bends around the sun, and so they look like they're here and here, and then they look like they're here and here, and then they look like they're here and there. And that area around the sun appears to be void of stars, not because it is, but because that light bends around the sun. Grace, go ahead.
Does this have anything to do with what black holes are?
Yes. All right. So, give me 2 more minutes and we'll get there. Okay? So, another thing that happens, and this is actually in the news the other day. I didn't show you guys the video. Maybe I'll show you guys the video on Tuesday. Okay? What ends up happening is our sun doesn't have very much gravity at all in the big picture. But let's say we have some really far bright object that puts out a lot of light. But it's far away, so it has to pass around something really big, like several galaxies. Several galaxies have a lot of gravity. Okay? So what happens is, some light from this star goes this way and bends here. Some light from this star goes this way and bends here. Following me so far? So what happens is, we see the same star in 2 places. They look exactly the same. Twin stars. And it would be the same thing like, okay, let's say there's a mirror here and a mirror here, and there's a person here, but there's like a wall right here. You know what I'm saying? You'd see the same person in 2 different places. Does that make sense? You'd see him over here and you'd see him over here, but it's the same person.
But why do you see?
Because this light bends around this way and comes here, but remember, the bending causes us to see the star to be over here.
Why is a distant object? How can it give off 2 areas of light?
It doesn't. It only gives off, well, these are like 2 separate beams from the same star. You know what I'm saying? Like, notice they both start in the same spot, right? It's light from the same star, but light goes in all directions. You know what I'm saying? So some of it rounds the corner this way, some of it rounds the corner this way, and we end up seeing the same thing in 2 different spots. Or, if you get enough light and enough gravity, you can actually see it in 4 places. Because it bends around the left and the right, but it also bends around the top and the bottom. Sunday night, this week, NASA released images from the Hubble telescope that look exactly like this. I'll show you the video on Tuesday. It's here, hold on. I'll show you the video right now. All right? It's actually a supernova, a huge exploding star. But we see it 4 different places at the same time. All right, ready? Here we go. You guys, it's actually kind of more like a slideshow than a video. I thought it was going to be more exciting than this, but it wasn't very. Okay. So.
Wait, how do we know that it's all coming from the same place?
It's so pretty.
True. Especially when you see this in particular. So. All right, ready? Here we go. Come on.
Wow.
All right, here we go. Come on. Come on, video. Okay. These images, they say. I know.
So how do they estimate that it's 9 billion years old? Or is that just like they want us to think that?
Not sure about that.
Yeah, but they can't figure
Well,
out how far.
if it's 9 billion light years away, that means that light has been traveling for 9 billion years. And as we kind of discussed yesterday, we're seeing that supernova as it was 9 billion years ago. And it's just getting to us now.
That means stuff is going around.
Yeah, well, 14 billion years-ish, right?
Oh, so what if they see something from the beginning of time?
Then that means we saw something that we're seeing something at the edge of the universe. Right? But the important part being, right, it's called an Einstein cross because this doesn't happen unless light is bending around massively huge objects that have a lot of gravity. And so, gravity affects light. But if you got enough gravity, right, as that light bends around that really huge supermassive thing, guess what happens? It doesn't bend around it because the gravity's too big. So what happens? Gets sucked right back in. And that's what we call a black hole. All right? Now, here's the problem though. How does it happen? Because according to Newton, this shouldn't happen. Because light doesn't have mass. But it does.
Ugh.
Say again?
You said that light doesn't have mass?
No, well, light doesn't have mass. But Newton didn't know what light was. Okay? But Newton said that gravity exists between any two objects that have mass, right? m1 times n2 over r squared. If light doesn't have mass, this shouldn't happen. But it does. Okay? I mean, I can tell you how, but we only got 5 minutes left in the period. So, all right, so here's what happens. Okay? Or do you guys want a cliffhanger for 3 days?
No, I won't go.
All right, so I'm not going to be here Monday. So, I told you guys I wasn't going to be here Monday at the beginning of class.
Tell the recording.
So,
Are we gonna get the Army now?
I don't know. The lady who's subbing for me, her name's Emily Sinclair. I can't remember if that's her or not. So, I think it might be. Yeah. So, I think it is. So, I'm just saying that's her. So, no, I know you shouldn't say that on the recording. So, all right. So, here's what Einstein says. Gravity is not a force as we think of other forces, or any force for that matter. All right, remember way back on the first day of this unit, we talked about that Einstein reevaluates the universe as consisting of time and space. Yes? Remember that? Space-time, really inventive name, blah, 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 right? So, universe is actually not a think of it this way. Think of the universe as a stretchy material, like a trampoline. Okay? If you step on the trampoline, what do you do to the trampoline?
Expand it.
Well, yeah, expand it and you make like a dent in it, right? If somebody heavier than you steps on the trampoline, what do? Except it's a bigger dent. What Einstein says is that the universe is made up of this four-dimensional entity called space-time that has the ability to be malleable, changeable. And that mass makes a dent in space-time. Things roll across the surface, right? There's no friction in space-time, okay? Things roll across the surface, and if the surface is flat, what do they keep doing? They just keep rolling. But if they encounter one of these dents in space-time, what happens? They fall in. Well, they go to the bottom of the hole. So, guess what? Earth's at the bottom of the hole in space-time. So where does this ball end up? Bottom of the hole. Okay?
Well, what happens when we're in the bottom of
We're at the bottom of the hole.
Because we're a mass. What do you mean
Because we're mass. Well, the Earth is mass too. The Earth is making a much bigger dent in the trampoline than we are, right? But we're making a dent in the trampoline too.
So we're in a black hole right now.
No. That's what Einstein says gravity is. It's a dent in the trampoline that things just fall into. But the heavier an object, the bigger dent it makes.
So we're making a dent in space-time.
Heavier things make bigger dents. A black hole is so heavy that it makes a really deep hole. Things that are going fast have the ability to sort of go into the hole and roll back out the other side. Right? If you have a hole, right? If you're rolling something fast enough, you can make it roll in and roll back out. Or like a golf ball going around a hole, right? If you sometimes you hit the putt and it goes around the edge but doesn't fall in. Right? That's something traveling so fast that it doesn't fall into the hole.
How fast is that?
Well, it depends on how big the hole is. A black hole is so deep that even light traveling at 300 million meters per second isn't traveling fast enough to get back out the other side.
So what happens when you fall into the black hole? Like if a star is in there, but it's just...
Flip, good.
So would time pass differently on how objects are at different
Yes. Tuesday.
I hate that.
Enjoy the weekend, everybody. So.